We're now going to talk about one of my favorite topics, which is recursion. But before we get into what recursion is and how we can use it, I'd like to offer a sort of motivational example because when you start learning about recursion, you might kind of feel like this. And that's because it's hard. Recursion is really difficult to wrap your mind around when you first see it. So don't feel discouraged if it's hard. That's normal. If you just pick it up really quickly and run with it, you are a very unusual person. For most of us, this is a very difficult topic, but once you get it and see the power behind it and the elegance of it, hopefully you'll be as enthusiastic about it as I am. So, onto that motivational example. Let's suppose we're going to transform our standard linked list. So our standard linked list looked something like this. Each one holding a value, and then the last one didn't have a reference to anything. Okay, instead of doing that, what we're going to do, and I'm going to draw this from top to bottom rather than from left to right. I'm going to draw a node, but this node's going to be a little different than the linked list node that we've seen thus far. This one's going to have two references. And we'll draw a few more. So this one's going to have a reference to this node and this node. And similarly, we could continue down in this fashion and say that this one has a reference here, a reference here. Maybe this one only has one active reference here, and then there's no reference over here, so we'll just X that out as we did with the linked list, and we'll X these out. This is just saying that they are at the end. Their reference is null. So we're not going to actually get in yet into what this is. This is a tree, a binary tree. We'll be talking about trees later. But in seeing how this simple addition to our node, as a kind of motivational example, we can help see why recursion could really be useful. Because now what I'd like you to think about, and it might be helpful to pause the video for a minute and really think about this. How do you traverse this thing, right? If I want to, let's say that each of these nodes has some number. Say something like that. How does one, say, go through all the nodes in this thing and, let's say, add up all the numbers? Okay, well, with a linked list, we could just have a while loop. We start at the first one, and then we just follow the references to the end. So it seems like we should be able to do something like that here, right? Okay, well, while, what are we going to call this thing? This thing here, I'm going to call the root. Yeah, I'm not going to get into what trees are yet, but the top of a tree is known as a root. Okay, so what are we going to do? While the root is not none, but what's confusing here is for every node that we traverse, there's two more nodes we have to traverse. And so even if I write while loops like without any conditions associated, just, kind of a general notation, it seems like for each while, do I need two whiles inside of it? And then wait a minute, because this could go down another level. Does each of these while loops need 2 whiles inside of it? And like, how do you even code something like that where there's like a variable number of whiles? Well, you can't. Doing the same approach that we did for this linear linked list isn't going to work. So one approach we could do would be to use a stack. And we'll see how this works more when we get to trees. But in essence, we can start by pushing the root onto the stack. And then since that's all that there is, we would pop it off and then push its children onto the stack. And we'd keep doing that until we had, say, pushed everything on a particular level or down a particular path. There's kind of different ways of approaching it. But using a stack, we could kind of keep track of all the nodes that we have yet to see. That is, if I traverse down here, I wouldn't forget the fact that there's still a node to be traversed down here and then nodes to be traversed down here. So with the stack, we'd be able to make this work. However, while that can work, we can write a more elegant solution to this problem using recursion. And so in general, whenever we are dealing with some kind of hierarchy, or maybe some kind of like nesting, where the definition of something is kind of within a larger subset of something else. Nesting and hierarchy are kind of related. Recursion is really useful. And so as an example with this linked list up here, we can think of this single node as a one element linked list. Similarly, we can think of these two nodes as a 2-element linked list. And notice how like this single one is kind of within this greater one of 2 nodes, and even further still, we could say that the whole thing is this 3-node linked list. And so, and every step of the way, if I were to iterate, change colors here so it doesn't get too confusing, but if I were to start here and then iterate to this one, we could say that everything from this node onward is still a linked list. And so as we kind of traverse through something, the definition of what we are traversing through is still intact. That is, the remainder of whatever is left is still the same definition as the thing that we started with. So that might have been kind of confusing, and don't worry about it too much, but just know that in general, when we have things represented as kind of this hierarchy, or there's this sort of nesting involved in the definition, recursion will come into play. So in the next video, we'll look at an actual Python implementation of a function that is written recursively.